Hi everyone, it's Michael. So I have another very nice problem for you guys today. This one is also posted by the same poster as my last problem, John LP1234. So I'm not sure where he gets his problems, but they're very nice problems. I feel like I might have seen another poster post this recently and no one replied. So this will be my chance to show a proof of it. So if you want to solve it, feel free to pause the video. Alright, so now I'm going to go over the proof. So we have the triangle ABC, and H is the orthocenter. The angle bisector of BAC meets side BC at D. The tangent to the circumcircle of ABC at A meets CH at P. PD meets AB at K, and we want to show that KH is perpendicular to AD. Okay, so how do we start off? So here's kind of my strategy. So since so first I'm going to let KH meet the angle bisector at point I. Okay, so basically we want to show that angle AIK is 90 degrees, but that would be the same as showing that AIHE is a cyclic quadrilateral because angle AEH is 90. So if we knew angle AIH is 90, that would mean that that quadrilateral is cyclic. So that would mean that angle KHE would have to equal angle IAE, which is half of angle A, since AD is an angle bisector. So basically we want to show that KHE is half of angle A. So how do we do that? Well, we can also notice that angle not only is so we want to show AEHI is cyclic, but we also know that AEHG is cyclic. So we know that angle EHB is equal to the whole angle A. So it's equal to all of angle ABC. So basically we want to show that angle EHK is half of angle A, but we know that angle EHB is all of angle A. So basically we want to show that HK is the angle bisector of angle EHB. But we can show that it's the angle bisector using the angle bisector theorem. So we want to show that HB over HE is equal to BK over KE. Now HB over HE, it seems like we can kind of get a handle on that because there's a lot of similar triangles in the figure. But how do we get BK over KE? And so my idea here was to use projective geometry and cross ratios, which I used to be scared to death of doing just probably a little over 2 months ago, but now I think it's just so awesome how you can use it all over the place. So we want to show that HB over HE is BK over KE. So how do we get that ratio BK over KE? Well, it's part of a cross ratio for the 4 points B, K, E, and A. So I'm going to try to calculate that cross ratio. So before I get into the details, I'm going to construct another point here. So I'm going to let BC, the line BC, meet the line PA at a point J. And I'll explain why I'm going to do this. Okay, so I'm looking at the cross ratio BEKA. So this would be BK over KE, because you look at what ratio does K divide the segment BE in, and then the same with A. And we want the ratio BK over KE because we want to use it in the bisector theorem. So how do we get this cross ratio right here? Well, you can see that you can project all 4 of the points through point P. That looks pretty convenient because all 4 points kind of lie on lines through P. So let's project them through P and onto line CJ. Okay, so if we connect P to point P, it obviously intersects the line CJ at B. If we connect P to K, it intersects CJ at D. If we connect P to E, it intersects CJ at C. And if we connect P to A, it intersects CJ at J. So from all this, from what I just said, projecting through point P onto line CG, we have that this cross ratio B, E, K, and A is equal to the cross ratio B, C, D, and J. And that looks a little more manageable because we know, we know a lot about points B, C, and D, obviously. And point J, that seems like we could probably get a handle around it because that's where the tangent at A meets side BC. That seems a little reasonable. All right, so now I'm going to try to compute these cross ratios. So just using the definition of cross ratio, you get this equality because K divides the segment BE and the ratio BK over KE. And A, it doesn't lie on the segment BE, but you can kind of think of it as cutting it into the ratio AB over AE. The ratio of the distances from the two endpoints of that segment. So when you divide those two ratios, you get this. And the same with these points. So D divides the segment BC in the ratio BD over DC, and J divides it in the ratio JB over JC, but you divide by the ratio. So you multiply by the reciprocal, and we have this equality right here. Okay. And we want BK over KE. So all these other ratios we have to solve for. BD over DC, we know that by the angle bisector theorem. BD over DC is going to be AB over AC. Now what about this ratio JC over JB? So we haven't yet used that JA as tangent to the circumcircle, and we're going to use it now. So whenever you have a tangent to the circumcircle like this, you create similar triangles. So first of all, angle JAB has to equal angle ACB. That's the property of a tangent line to a chord. Okay. The angle between a tangent line and a chord has to be the angle of any arc or any other inscribed angle that intercepts that chord. And so that's enough to get a pair of similar triangles. So that means that triangle JAB has to be similar to triangle JCA because they both share one angle. JAB is ACJ, and they also both share this angle AJB. So those two triangles are similar, and so the ratios of their corresponding sides have to be similar. So JA is a side of triangle JCA, and JB is the corresponding side of triangle JAB. So JA over JB, those are two corresponding sides in the two triangles. And that has to equal JC over JA, because both of those are the longer sides in these two similar triangles. And then if we take the medium-sized side, the ratio of those two in these two similar triangles also has to be equal. So for triangle JCA, the middle length side is AC, and for triangle JAB, the middle length side is AB. So these two ratios have to equal AC over AB. So ultimately, I want to get this ratio JC over JB, and so I can do that by multiplying the first two. So the product of the first two has to be the square of the third one. So that gives me this fraction right here, JC over JB. Okay, so now we pretty much have everything that we want to calculate BK over KE. So if you combine all this equation with this equation and this equation, well, on the right side, we're taking AB over AC times the reciprocal squared. So that would just be AC over AB. So on this side, we have AC over AB. Here we have AE over AB. So if you do the algebra, that means BK over KE is AC over AE. Okay, but we have a lot of similar triangles in this figure. So AC over AE, well, triangle ACE is a right triangle with angle A, and so that has to be similar to triangle BHE, because like I mentioned a long time ago, we know that AEHG is cyclic because it has two right angles. So angle A has to equal angle BHE, and so triangle BHE is also a right triangle with angle A. So I'm going to make some more. So AC over AE has to be BH over HE. Okay. And in fact, this is exactly the angle bisector theorem on triangle BHE. If BK over KE is BH over HE, then that means HK bisects angle BHE. So now we're very close to solving the problem based on what I said before. So I'm going to make a little more room for everything here. Okay, so HK bisects angle BHE. So that means that basically, like I said, angle BHE is equal to angle EAG because we know AEHG is cyclic. And so that means that KHE has to be half of angle A. So EHB is equal to angle EAG. So if you cut both these two in half, half of EHB is EHK, which we just found by the angle bisector theorem, and half of angle BAC is EAI, because AD is an angle bisector. So EHK equals angle EAI, and that means that EAIH has to be a cyclic quadrilateral because one of the angles is equal to the exterior of the opposite angle. So AEHI is cyclic, and so that means angle AIH has to be 90 minus AEH, or 180 minus AEH, which is 90 degrees. So AIH is 90 degrees, and that means that KH is perpendicular to AD, which solves the problem. So I hope you all like this. I'm starting to get a little more confident with projective geometry, although I did try to figure it out. There is a way to do it using Menelaus's theorem. So if you want, you could try to figure that out. A lot of times problems that can be solved using projective geometry can also be solved using Menelaus's theorem. So if you're too scared of projective geometry, you can always go that route. So if you like this video, please give it a thumbs up. And if you want to see more videos like this, feel free to subscribe to my channel. Thanks, everyone.